Okay, extreme values what was it, of functions on closed intervals. And I have a bunch of notes, or 4 pages of notes and examples I hand out everybody in class, but I'll post those when I upload these stuff. So we're going to do all these things today. All right. So what does it mean by extreme values? What do you think extreme means? No. Good idea though. Maximum, minimum, yeah, extremes. The highest, lowest, minimum, maximums, yeah. And that's what we're going to look at here. We're going to use calculus to find the extreme values. So we're going to look at maxima versus minima. This is the plural of maximum. Maximum, this is the plural of maximum. That's the plural minimum. So we have certain types. We have absolute. We have local and relative. Actually, there's one other one. There's global. If I can put those on your sheets, yeah. Now, mathematically, algebraically, how do we know something's a maximum? So let's look at a graph. If we have a curve like this, how do we know that this point here at C, this is f of C, how do we know that's maximum? Algebraically, but we can't do derivatives. What's happening here algebraically? Because you have to approach, when you're looking at what we did with derivatives, you're looking at both sides. As you're approaching this value C from the left, you have x1, x2, and so on and so forth. All of these x's are less than f of C. Same thing for these. For all of those x's, those functions are all less than f of C. That's how you know you have a maximum. How do you know you have a minimum? Same reasoning, but the opposite. F of x is greater than all f of C. All of your x's are greater than f of C. For all of the x's on your domain. Absolute and global pretty much refer to the same things. Absolute and global means overall. Absolute, extrema, over all points in the domain. But we can look at relative and local pretty much as the same thing. So absolute, in other words, if we had y equals x squared, since the domain of the x squared function is negative infinity, positive infinity, that means at 0, we have an absolute minimum. Or we say it's a global minimum.
Because the domain is all reals.
Right. And there's no other point lower. No matter where you look on the domain, there's no other point lower.
And that's known as a global point.
Absolutely right. Because there's nothing. Now, let's say we have y equals a cubic function. That looks like this. Where we have at C1 and C2. These are called local or relative maximum and extrema because it's only on a subdomain of the entire domain that it's true. So this is a relative maximum, or you say it's local because it's of that locality, whatever our small subdomain is. And this one here is our relative minimum, or our local minimum. Why are they not absolute? Because the graph goes on infinitely, both directions. We don't have an absolute in that case. So in other words, whenever our degree is odd, no absolute. Because when the degree is odd, our end behavior is opposite directions. The degree is the highest exponent. And they always have both ends pointing different directions, going to infinity, negative infinity. But they do have relative or local max extrema.
I don't absolutes.
No, because on odd degrees, they go opposite directions. They can't be absolute because any number you give me, I can just add 1 to it and now you don't longer have maximum or absolute. Because of these end behaviors going infinitely. Can you have a relative? So in other words, if it's even, if the degree is even, then you have an absolute maximum minimum. Can you have a local or a relative maximum minimum if it's even? Yes. Absolutes can also be relative or local. Because even if I took the domain right here, it's still in that subdomain, it's still the maximum or minimum, it's still the extrema. So that's why it does matter whenever we have, that's why in this section, we're looking at closed intervals. Because if we had a closed interval on a cubic function, we can have absolute maximum minima for that entire domain.
So if your function can, if its domain can exist for all real numbers, then it depends on what specific interval you're looking at.
Right. If I look at, so yeah, if I look at it over the entire domain, then we have an absolute. Either we do or don't, depending on the degree. So let's look at our examples. Example 1. The absolute extrema of the following functions on their domains can be seen in the figures below. Each function has the same definition equation, the y x squared, but the domains vary. So this one, the domains from negative infinity to positive infinity. So the first one, A, is from negative infinity to positive infinity. Do we have an absolute extrema? Where? You know, we have an absolute minimum at x equals 0. There's no absolute maximum. Now, the second one, the domain is from 0 to 2. Do we have absolute maximum minima? But remember, we've now changed it from negative infinity to positive infinity. Our domain now is from negative or from 0 to 2. So that's the entire domain.
So the maximum.
So we'll have absolutes, maximum and minima. We can also call them locals, but these are also, we're only looking for the absolutes right now. So we have an absolute max at 4 when x equals 2. We have an absolute min at 0 when x equals 0. Now the third one, we have an open at 0 and closed at 2. So do we have a maximum and a minimum?
Just the maximum.
Right, big Y.
Because
We can't get to the bottom, right? So we have an absolute maximum at 4 when x equals 2 and no absolute minimum. And the last one is open parenthesis on both of them. Since they're open, we can't count the endpoints. So what does that mean?
Well, wouldn't it would still have it? Just wouldn't get it.
No absolute extrema. Why? Because if we remember, the open circle means we can get infinitely close. So any decimal you give me at 1.9, I give you another 0.99, 0.999, so we can never get to it. That's why if you notice in our closed interval, which is what this section talks about, if we have a closed interval, then we have extremas. We cannot have them on open intervals unless it's an interior point. Unless the extrema happens on interior points. Because if I have my extrema from -2 to +2, and they were both open intervals, if they were both open intervals, I would still have an absolute minimum, but not an absolute maximum.
It would just be on the interior one.
Right. So basically, extrema points can happen on interior points or at endpoints. Let's okay, where's the rest of that stuff? Did I give you theorem 1? Oh, okay. I didn't give you theorem 1, which is the important one. Theorem 1, which is the extreme value theorem. Or did I give you? Where did we do those? Oh, well, I'll give it to you anyway. The extreme value set. The function f is continuous on a closed interval AB. Is it if f? Then f has both an absolute maximum and absolute minimum. In the closed interval. Did I give you those things? I could have sworn I gave you the first theorem also. I just gave you definition. Sorry. Okay. Now, why is that the case? If a function is continuous and it's on a closed interval, why do they have both absolute maximum and minimum? And can you find me a counterexample that doesn't work?
I guess because points. Those endpoints don't necessarily have to be maximum.
Right, as an x squared. But give me an example where you don't have a maximum or minimum. Or the maximum and minimum are the same thing. you have a constant equation, it's the maximum and the minimum, no matter what, because the domain is from negative infinity to positive infinity. Even if I give you a subdomain, it's still gonna be the same values. So does it have a maximum minima? No. Because in order to have maximum minima, remember you have to have this. Or at F value C. So since you don't have that, they all equal the same thing. Yeah, even though I said this is a continuous function, it is a function. So that's exactly, yeah. So let's see, I gave you also how to find extremos, and relative extrema is just those. Local and relative extrema is just those, the definitions. Local extrema is a point within in a subdomain in some open interval containing C. The reason it's open interval because you're not, it can be, if your domain was from negative infinity to positive infinity, but I gave it into some open interval just short of infinity. Why, once you have this, once you have an open interval somewhere inside there, you now have bounds, which means you can have a local maximum minimum. And that's what this is saying. Yeah, so by definition, a function has a local maximum if the point C is within a domain, f of C is less than equal to f of C, f of x less than f of C, for all x lying in the some open interval containing C. The absolute are in the closed interval containing C. And here's the different differentiations of them. This is a local maximum. This is also a local maximum. This is a local minimum. But the local maximum minima are those because they're higher than everybody else.
So the local maximum can be less than the absolute maximum.
The local maximum has to be less than absolute. Has to be less because absolute is the highest of all of them. Over the everything. Yeah.
And then the local is the highest.
But see, there's absolute no greater value of x anywhere. But it could also be a local. Right. Right. Because I could now have a closed interval where that point exists.
So if like, let's say we have the function, it's defined over the entire interval of all real numbers, f of x equal x squared. Then if we restrict the domain to like 100, negative 100 to 100, then we would have our local maximum and minimum points. And then over the actual full domain of all real numbers, there would be the absolute maximum
right.
and minimum. Okay.
Right. Okay, so how do we find the extrema points? As you said it earlier, now we're using calculus because you have a maximum at the highest point or a minimum at the lowest point. Those are the vertices. The slope at those points are 0. So to find the extrema points, steps Step one. Find the first derivative. Set the first derivative equal to 0. And solve for x. This point here is called the critical point. I'll give that to you also. Yeah, on page 3 of the sheets I gave you. Because where can this happen? You can have an extrema at interior points or endpoints. And the x values where that equals 0 is called the critical value or critical point. The critical point of f, if we want to be precise. Let's look at these points. Let's look at those two functions. Find me any extrema points there. So how would you find it? What would you have to do first? First derivative. So the first derivative of the first one is what? Then what do? Set it equal to 0. Then solve for x. Divide by 3. And then square root both sides. So x is at 0. Which, what does this function look like? It looks like this. It looks like that. So we're saying at 0, there is a horizontal axis. But is it a maximum or a minimum? Right.
Well, because there are, I mean, it's an open interval. there are other points that are higher and lower.
Remember how we talked about when you first said take the first derivative had to equal zero? You're absolutely correct there. But remember, when we talk about derivatives, we talk about limits. If we take it, remember, we have to have these. F of x is less than or equal to f of c. If this is true, if f of c is bigger than all the x's, that means this is a maximum. That works on these. But for these, all the f of x's are bigger than the f of c. So we have a maximum from the left and a minimum from the right, and you can't have that. If you have a maximum or minimum, it has to be from both directions. So there's no extrema on this one. How about the next one? Take the derivative of the cube root of x.
One of three.
Cube root of x squared.
Right.
Can you set it equal to zero?
No, we do five.
In a fraction, the only thing that can set it equal to zero is the numerator. Since the numerator is a constant, it can't be. So again, there are no extrema. What does this graph look like? What does square root of x look like?
Well, so it's gonna be all positive. Because no matter what you put in.
For x, for this one.
Right.
So what's the smallest you can have?
One,
Zero.
zero.
Square root of zero is zero. Square root of one? One. What's the next x you'd put in there? What's the square root of two?
Uh,
4. What's the square root of 4? 2.
oh, wait.
It looks like this. Square root of 4 is 2.
Uh,
Then you do square root of 9, that's 3. Square root of 16 is only 4. So the horizontal distance moves greater than the vertical distance. So the cubic function looks like this. It's the same as this one, just flipped. It's now lying sideways. The cube and the cube root are the S shapes. And this is, yeah, it has 0 there, but it's a vertical, and that's not what we're looking for. So there's no extrema of either one of those. When we do find a function that works, we can take a derivative of and we can examine. To find an extrema, you have to first take the first derivative of the function, set the first derivative equals 0, and solve for the critical points. And then what else?
Then you have to look at if you have to look at the inequality for f of x and it.
Examine the endpoints. Because will the first derivative be zero at the endpoints? No. That's why we take the endpoints. We take of our closed interval, we find f of a, we find f of b, and our critical points. And we find the largest and the smallest of those. Oh, good. Turn your sheets over and we have examples now. Yeah, it should say page 4 on the bottom. Find the absolute maximum minimum values of x squared on this closed interval. Oops. So how would you do it?
Find the first derivative of x equals, or f prime of x equals 2x.
Set it equal to 0. So x equals 0 at 0. So we have at x equals y equals. At x equals 0, y equals 0. So that's the first thing. That's our critical value, our critical point. Now we look at the endpoints. When x is -2, y is 4. So it's -2 squared, which is 4. When x is 1, y is 1. All we have to do here is look at the y values. This is the minimum, and this is the maximum. Because it happens inside the domain, or within the bounds of that domain. So we have a absolute minimum at 0, 0, and we have an absolute maximum at -2, 4. Do the next one. Find the absolute values of f of x equals 10x times 2 minus ln x. So we're gonna use the product rule. What's the derivative of 2 minus ln x? You guys forgot what the derivative of lnu?
Oh, yeah, it's 1/L.
Yeah, ln 1 over x. It's du over u. So this one would be negative 1 over x. So the derivative of ln u is du over u. So we have 10 times 2 minus ln x plus, I should be minus 10x 1 over x. The x's cancel. So we have 10, 2 minus ln x minus 10. Set that equal to 0. And then solve for x. So when is ln x equal 1? How would you solve that?
Oh, the E.
E. So this is log base e of x equals 1. So it becomes x is equal to e to the first power. So x equals e. So we have a 0 point when x is e, y is 0. So what else we do? Oh, no, this is when x is e, we have to put it back in the original function to find the value. This just tells us our slope. So when x is e, we have 10e 2 minus ln e. Ln e is 1. So when x is e, we have 10e. That's one of our points. Now we have to check the endpoints. When x is 1, we have 10 2 minus ln of 1, 10 2 minus e. No, ln 1 is 0. Yeah, that's 0. I said this from x. So it's 20. So 120, there's another point. And we check the other endpoint when f of e squared. 10e squared 2 minus ln e squared. Then e squared 2, bring the 2 down. Ln e is 1, so it's 0. So our points are x values and our y values. When x is e, we got 10e. When x is 1, we got 20. When x is e squared, we got 0. Do we have a maximum? Do we have a minimum? What is e? What's the value for e? 2 point something. Is it bigger than 20? So 10 times 2 point something, 10 times 2 is 20. So 2 point something is bigger than, so this is out of the question. So this is our max. This is our min at e squared. Make sense? Yeah, I'm sorry earlier. It's once you find the values, plug it back in the original equation to get the y value. Because the first derivative just finds us our slope, and we know it's 0. So that's what we should be doing.
So. Okay, I see that. So, yeah. Okay.
And this is where you have to remember your ln and your e rules. All right, the last one. Find the absolute maximum minima of the values f of x equals x to the 2/3 on that closed interval, on the open interval, or closed interval. That should, that's the last one. What's the derivative of x to 2/3?
2 over 3 times the cube root of x to the power 5. So, right. I don't know, it's what.
If we subtract 1, which is 3 over 3. So set this, there is no place where there are no critical values. So we can't set that equals 0. So we check the endpoints. F of -2 and F of 3.
So if you have no critical points, then you go to your end.
Well, you always go to endpoints. You always check the critical points and the endpoints because it's got to be some of those. So, yeah, we have to check all 3 of them. And that's why we're dealing with closed intervals in this section.
So at your critical point, f of or f prime of x equals 0, you can have a extremum, and then you can also have them at your endpoint.
Right.
Okay.
Any one of those 3 points, right?
But in this case, we don't have a critical point.
Right. So we know it's got to be at the extremos. I mean, at the endpoints. So -2 squared is 4. The cube root of 4. When x is -2. And this is the cube root of 9. And we know it's a continuous function. So we have our, well, actually, do we know for sure that that's our lowest point? Yeah, so we put -1 in there to see if that one's any bigger or smaller. 1 cube root of 1. At 0, 0, 0 is smaller. So we have to now check those points.
So f of 1. Or no.
Right.
Yeah.
So we have our x and y values. At -2, we have the cube root of 4. At 3, the endpoint, we have the cube root of 9. So at -1, -1 squared is 1, cube root of 1 is 1. So same thing at 1. At 0, it's 0. At 2, it's the cube root of 4.
So we do, so those are.
So we have our minimum here, which is and the biggest value we have outside of that is the cube root of 9. So basically what I think this graph looks like is like that.
So it's x approaches 0.
It's a decreasing function.
Right.
And same thing with the right. It's a decreasing function. Because this, remember, the cubic function normally looks like this.
Right.
When you square it, you just make all these positive now.
And then are you reflected across the x-axis?
It reflects because it's squared, right? In other words, this answer can never be negative. So we flip it over the x-axis.
So it really helps to know what these graphs look like.
By all means, yes. That's come in algebra. In the second or third week, I give them a library of functions. Memorize those because if you ever, actually, I'll give you those sheets next time,
Okay.
and we'll go through all the library of functions.
College algebra.
No, I have a sheet with all 12 functions,
Okay.
and we'll give you the domains. We'll give maximum, minimums, everything.
And then once you know what those look like, it really helps you.
It does. It very much so, because just by looking at it, you can tell exactly what's going on. Because the function here is x to the power 1/3. Because x squared is not going to be it because it's a rational. So it's 1/3, which is this graph. And basically what we have here is x to the power 1/3 squared, which means everything is now positive.
Right.
So yeah, even though these weren't extrema points, we have to look at those to see what's going on. What does the graph look like? And the behavior of the functions. Okay, that does it for that section.
Well, that's nice. It's not as long, so.
No, it's actually I should have gone ahead. Well, what's the next topic talking about? That's chapter 8. The mean value, Rolle's theorem, I don't want to skimp on those because these tell us like the mean value theorem, intermediate value theorem,
The mean value theorem.
and Rolle's. They're important. They're pretty straightforward, but they're important. So we'll do that one as well as we'll try to do section 3 also next time.
Okay. Okay.
All right. So that's it for today.
The mean value theorem, that's used in statistics as well, right?